This is a TS diagram of our Rankine power cycle. It uses ammonia as a working fluid because ammonia reaches supercritical at a relatively low pressure, specifically around 11.3 megapascals. Supercritical fluids are useful because they allow, in this case, the ammonia to undergo large changes in density with a pretty small change in pressure and temperature. This is good for turbines in general. If you notice in the graph, we have one isobar from state 6 to 1 that is on top the curve, and that's because the ammonia in these states is actually supercritical. The other isobars are P equals 3.4 and P equals 0.7. In general, the shape to the right with the zigzag is a little bit unusual, but that is just simply because we added a second turbine to our system. The reason we did this is because it allows us to increase the temperature of the working fluid and, more importantly, increase enthalpy at state 3. Since the second turbine will therefore have a larger drop in enthalpy across it, hopefully this would mean that it would output a larger work magnitude.
When deciding on the model of our Rankine cycle, we had the option of using multiple turbines in order to increase efficiency if we saw that that would improve. When we were able to add more turbines, we had the option between a new turbine stage and a refurbished turbine stage. The new turbine stage had a higher isentropic efficiency of 0.87, while the refurbished turbine had an isentropic efficiency of 0.8. Now, the difference between these two was the new turbine was double the cost of the refurbished one. So it would be $5 million per turbine for the new one and only $2.5 million for the refurbished ones. So we had to keep this in mind when we were testing our data to see whether the greater isentropic efficiency would help us out, or if the greater cost of the turbines would be too much for us to bear. After doing some trial and error, we saw that using the turbines with the higher isentropic efficiency yielded a better overall efficiency, while increasing the price to $9 million for the two turbines. However, with these two new turbines, we were able to get an overall efficiency of about 42%, which is 3% above what we were going for, which was 39. Therefore, we decided to use the new turbines despite the fact that they cost more than the refurbished ones. After we determined that we were going to use the two new turbines, we needed to work out what we wanted our pressures to be for the three isobars. We first decided on P equals 40 for our supercritical pressure, and then we wanted a low pressure that was pretty close to the bottom limit, which was 0.06 bar. We decided on 0.07 bar. So the middle pressure was what we had to figure out in order to optimize efficiency. So with some guessing and checking, we noticed that values between 0.1 bar and 10 bar were yielding the best efficiencies for our overall cycle. However, we wanted to get a more accurate reading on what we thought would be the optimal P2 value. Therefore, we did a parametric study with P2, comparing that to the overall efficiency. So as you can see from the parametric table and the graph, the optimal pressure for our middle isobar would be around 3.4 bar, which would yield an overall cycle efficiency of 42%. Now, 42% is over 3% greater than 39%, which was the goal we were looking for. So we ended up making approximately 30 million 30 million because we were 3% above 39, and then for each percent above 39 you get an extra 10 million in profit. So after doing the parametric study, we were able to get a an optimal P2 value, which was 3.4 bar. And then after calculating the cost of the entire turbine, which was 8.1 million, and then the total we would make from being above efficiency, we made 31.6. So our overall cost benefit would be the difference between those, which is 13.5 million, which is a very good number for this cycle.